tension acting over here. Okay. Tension. So the red is the tension in the cable. Okay. So T equals cable tension. Okay. Now this was a beam. Okay. In addition, I'll just draw it on a erase very quickly. This was a beam. Not only would I have a tension, I also have a bending moment over here and a shear force. Okay. When I cut the cross section. Okay. The assumption over here is that it's a perfectly flexible cable. So what I have is the tension at A and the tension at B. There's nothing that the book doesn't mention. When I go and I traverse the cable, to say from point A to point B, is the tension constant? The answer is no. The tension will vary, as we see, with the arc length or with X as we go from A to B. Okay? The book doesn't say that. Okay? So just throw the final equation, okay, which involves a lot of assumptions. Okay. So T is the cable tension varies along the cable. Okay? Let's introduce another angle over here. It will be a theta, like a slope. Put this obviously, there's a theta down here also. So theta is simply the angle made between the positive x-axis and the red tension vector over there. That's your tension vector. Okay. And clearly, I've got one over here also. Okay. So what I'm going to do now is write down the equilibrium equations. Okay. So first we have, remember this is just hanging equilibrium. So there's two equilibrium equations, right? There's equilibrium along x and equilibrium along y. And to make the problem even more fun, okay, the cable has a weight on it per unit length. There's a loading on it. Okay. I'll put this like here. W. W is, so we should define W. So W is the loading per unit length on the cable. Okay? Most probably is due to the weight of the cable, and maybe you have some birds sitting on there too, right? What's nice is we can absorb both of them in this function W. Okay? So long as you can describe W analytically. Okay? W is the weight per unit length. Okay? I think now we've got everything, right? We've got the weight per unit length, we've got the tension in the cable, the angle. Okay. So let's now do equilibrium along the x direction. Okay? Sum of the forces along the x direction. Okay? Now remember, I said that tension is varying in the cable, right? As we go from here. There's no reason to assume that the tension at A and tension B are the same. It's obvious, based upon your physical intuition, that theta doesn't varies along the cable, right? Here theta is very shallow, then it goes up here, right? That's what gives it curvature, right? Theta can't be constant. So C and theta both vary along the cable. But what can we say? It's an equilibrium, okay? So therefore, here's my system. It's just a cable between A and B. I sum all the, remember what Newton's law says. Okay, people, let me say this correctly, okay? It says that based the body's in equilibrium, then the vector sum of the external forces acting on that body must be zero. And it's very important to say external, because depending on how you do the diagram, internal and external are different. If I looked at the whole cable, then the only external forces are basically at the supports over here. But as soon as I take that section and lift it out, now the internal tension becomes external to that system. Okay? So, sum of the forces along the x direction. I've got tension, cosine theta evaluated at B, minus the tension, cosine theta evaluated at A is equal to 0. That's equilibrium along the x direction. And remember, both T and theta vary. What's very interesting, though, is what's in words, what's T cosine theta? Is that just the horizontal component of tension, right? So I take a finite segment between A and B, and I don't care how big it is, okay? I find that T cosine theta evaluated at this what's interesting is that T varies, theta varies, but the product T cos theta is a constant. And that's the horizontal component of tension, which you can actually compute if you know how to, from some empirical data. Okay, so assume we know that fact. Okay, now I've got equilibrium along the y direction. Okay, this goes positive up like that. Well, what happens here? T cos theta along x, T sine theta along y. Okay? So now I've got T sine theta evaluated at B. Okay? And now, of course, if I do it over here, it's T cos theta with a minus sign because it goes down, minus T sine theta evaluated at A. That's basically the forces along the y due to the tension. But don't forget the loading, right? And that's minus. So it's minus W delta S is equal to 0. Now let me just say something about W, and be precise about this. I'm going to put W of S prime delta S equal to 0. I'll tell you a second what W of S prime is. If W was a constant, suppose like it was just a uniform cable, I don't know, maybe it had like 3 pounds per foot, then you wouldn't need, W wouldn't be a variable, right? It's just 3 times delta S. But suppose that the loading varies along the cable. That can happen. It may not be a uniform cable. But some bridges, basically, maybe they start off very thick and then they taper out someplace. Or imagine there are more birds over here than sitting over there. So the W varies with arc length also. And the question is, what's this S prime? Okay, well, just imagine, okay? I got W along section AB. It's obviously going to assume a minimum value and a maximum value. If I take the minimum value for W multiplied delta S, I've underestimated the load, right? So it's too small. If I use the maximum value of W, I've overestimated. And by mathematics, assuming that this thing is continuous, there will exist a point S prime such that this gives the exact load. And the only thing you know about S prime, this is the intermediate value for calculus, that S prime lies between S and S plus delta S. Okay? Where S is the arc length here, and S plus delta S is the arc length over there. We're going to take the limit as delta S goes to 0, so that S prime is going to go to S, so we actually don't even have to know it. The thing that's important is that it's somewhere between S and S plus delta S. Okay? And that's only in the case where the load varies with the position along the cable. Okay. So this is, I'd say, typical of what you do to get equations, be it for beams or cables. You basically write equilibrium equations, okay? And then you want to get a differential equation. What I'm going to do now is take this equation, divide by delta S, okay? And let's see what happens, okay? So I've got T sine theta evaluated at B. Let's go to S plus delta S, okay? So S is the arc length at A, and S plus delta S is the arc length over here. Okay, remember calculus, where you measure S equal to 0 from is immaterial. The important thing basically is that this thing is delta S away from here. And this is arc length measured, if you took a tape measure along the curved beam. It's not just the projection along X, which is what the book does. This is the actual cable length, okay, in feet if you measure it. Okay. So we got T sine theta evaluated B, or arc length S plus delta S, minus T sine theta evaluated at A, which is S, divided by delta S, minus W of S prime is equal to 0. Okay? Now I'm going to take a limit as delta S goes to 0. And all you have to remember is the definition of derivative in calculus. Remember, if I have a function of S, by definition, the f dx for calculus, well, you can probably remember the f dx is basically the limit as delta S goes to 0 of f of S plus delta S minus f of S divided by delta x. Hopefully you remember that. This is the definition of the derivative. Week 1 of the calculus course, right? Okay. What's my f of S over here? It's just T sine theta, right? Substitute for f of S, T sine theta, what do you have? Limit as delta S goes to 0 of f of S plus delta S, T sine theta, S plus delta S, minus f of S, T sine theta S. Okay? So we take the limit, this becomes d by ds, arc length, of tension, which varies with the arc length, theta, which varies with the arc length, is equal to little w of S. Now, why do I write W of S, not W of S prime? Because S prime was between S and S plus delta S. As delta S goes to 0, S prime goes right in. Okay? Not very useful, though, in this form. Okay? But what we're going to do is eliminate the tension. Okay? And the way we're going to do that is use, I should move the box around not too useful because you want to have a single variable independent of one dependent variable, okay? When you write dy dx, you think of y as a function of x, and that's exactly what I want if I want to get the shape of the curve, right? I want to get y versus x, so I can plot it, okay? But this has this crazy d by ds. So we're going to have to use a formula for calculus from the chain rule, okay? So, for chain rule, okay, the derivative of an arbitrary function f with respect to s is what? It's df dx times dx ds. Right? This is the chain rule. This relates the rate of change of a function as with respect to arc length versus with respect to x. So you get this factor of dx ds by the chain rule. Okay, so let's plug that in on the left-hand side. So as having d by ds of that thing, I'm going to write basically like that dx ds times the derivative with respect to x of dy dx. That's much better. Everybody see what happened over here? I got d by d. I got f is now y prime, so I get a dx ds times the derivative of y prime with respect to x, which of course is just y double prime, right? And the right-hand side, I'll have the w h. Let's just simplify this. I've got the second derivative of y. I've got the second derivative of y with respect to x. So it's a second order differential equation. Looks like I got the weight that can be a function of x or s with an h times ds dx. Almost there. Just one more step. Okay. Now again, this is something which there's certain things from calculus I expect you to kind of have on your fingertips, like the chain rule. I don't expect people to remember the formula for arc length. The standard thing in any calculus course, you should have done this, is they'll give you a curve y equals some function of x. Say, find the arc length. Okay? And you'll need that formula for arc length. And I'll just say, recall from calculus. Okay? I got this thing, ds dx. Simply the square root of 1 plus y prime squared, or y prime is 1. This equation has become nonlinear. Okay. So finally, the differential equation, when we're finished, is the following. The second derivative of y with respect to x equals w over h, which I know, ds dx, the square root of 1 plus dy dx. That's a final equation. The table, we'll just check that you make a mistake over here. Yes, that's fine. Now, what can we say about this differential equation we write? It's a second order differential equation. It's got the 1 over prime rule, right? And it's nonlinear, unfortunately. It's got the square root of 1 plus dy dx squared. Okay, to actually solve this equation, okay, we're not going to do it today, okay, we'll do it later on. Okay, we'll make a simplification at this point. And also let's ask ourselves about, go back to the physics of this. In order to get a unique solution for that equation, assuming it exists, which it does, it's a second order, so I need two conditions, right? Now this is what I call, remember, it's a boundary value problem, right? Because you have the value of y, say at x equals to 0 maybe, right? Maybe this is x equals, I don't know, x equals L or something like that, okay? You got the distance between these two poles. You know this point to support, and you know that point to support, right? So therefore you have two conditions, one at x equals to 0 and x equals to L. That's a boundary value problem, right? Right? Not an initial value problem where you have the function's derivative at a single point. The physics of this thing is the boundary value problem, because you know where the cable is suspended. So hopefully you could solve this, okay? You'll get two arbitrary constants in the general solution, and then you'll apply these boundary conditions to evaluate them, and you'll have the curve, and then you can use MATLAB to actually plot it. And if you do things right, it is going to look like that, okay? You get the exact shape flow. Okay. What's interesting is that, just as a side information, is that when a cable hangs under its own weight, it hangs in a cable, it's called a catenary. Okay, like a cosh, hyperbolic curve. Okay? But in our case, W can include the wave unit length of the cable. It could also be other stuff on there. There's some other external load, wind load, for example. Okay, so the question is now, how can we simplify this? Okay, and this is basically one that the book presents. See, it's a lot of work.